Hello, welcome everyone. Welcome everyone conference course on embedded memory system programming. We'll have a short intro about this course. Actually, this course is offered by HCL Tech as a core LLP for PE, ECE, and EE students of this semester. It's highly industry-oriented subjects where it tends to bridge the gap between academic and real-time embedded product development process. The modern era system automation using IoT, industrial control, robotics, and industrial automations. The role of embedded systems forms a technological backbone for almost every digital platforms. As increasingly, uh, industries are being getting adapted to the space technology. Fairly, it is necessary and need for the engineers to strong expertise in programming system programming. Hence, this subject acts as a mandatory training charge for aspiring members from developers and further engineers. This course will be introducing the students towards the architectural programming concepts and the team of the designing and implementing mobile applications. Very close to the hardware and maintenance of the efficiency related. Practical knowledge of embedded programming and along with mechanical interfacing Linux-based concepts will be discussed in these subjects. Along with the most important thing is the process management, thread management, principles, etc. As you can see in this figure, we have this user space, kernel space, and knowledge space. Our significant focus in this unit will be on the kernel space, where we will be writing the C programming, focusing towards hardware access through the kernel operations, like process management, process management, and thread management, etc. The kernel space will be found the core of Linux operating system and will give the privilege to access the system resources. The kernel will be acting as interface between the software application and the user space and the hardware parts. And here, as the embedded C developers, we must have a thorough study of Linux system programming, the kernel operations, and students will be gaining valuable insights on how the operating system manages hardware efficiently for stable execution of embedded application. So, without further delay, let's get into the subject. Here, actually, you can see the concept of the codes where the unit will focus on embedded C programming, and we'll be having a clear-cut distinction between how it is being particularly used for embedded applications, followed by the microcontroller programming. Here, we'll be discussing almost some part of this already discussed, like HDP, vice versa, USB, what, etc. Then unit 3 will come into the core part of the unit subject Linux system programming, where we'll be elaborately dealing with the user space, kernel space, process management, thread management, etc. Unit 4 will be focusing on the interprocess conversation, shared memory and CPU types, kernel sockets. And in unit 5, we'll be discussing about multi-threaded programming and how different scheduling operations are being done for real-time processes. We'll be moving up to unit 1. The unit 1 is on embedded C programming. We'll have a short overview about what is being what we're supposed to discuss in this unit. So this unit will be acting as a foundation pillar for understanding the software development in embedded system. Okay, since now already there is students have a fundamental knowledge on C programming, this unit will be giving an extended learning towards system-oriented and hardware-aware programming concepts. Okay, the unit will be covering the core programming concepts like the variables, construct, control statements, arrays, pointers, etc. Those things we have already discussed. So our main focus of discussion initiated will be from the memory layers, especially starting from the memory layers, and how it things significantly used in embedded programming, and how the memory organizations are being used for managing embedded system resources. So that will be discussed. So this unit will also further highlight about the arrays, pointers. So those things might have studied in the data structures. and these things will be the debugging methods, we're going to use these things to discuss. And we will refer the concepts of data structures, basic functional etc. And core for a real-time system, embedded system developer, what are the functional requirements, non-functional requirements, so that things also will be discussing in this. Okay. So before getting into this topic, the embedded system topic is one of the fundamental difference between embedded C programming and conventional general purpose C programming. Okay, focusing on embedded C programming, it is designed specifically for hardware-oriented applications such as microcontrollers, IoT devices, automation systems, etc. So it provides the efficient memory management, where it is a very critical thing in embedded system, which has limited resources and storage, limited RAM and storage access. Okay, so here direct interaction, hardware interaction through registers enables precise control of peripherals like the GPU, SP, and sensors, which cannot be achieved through conventional C program applications. Further, embedded C also supports real-time execution capability, which is an essential in terms of time sensitive, automotive, robotic, and industrial application. So, this is also one of the major why we need embedded C. Then, when we're looking at the hardware specific libraries and tool chains, depending on what hardware you're choosing, specific hardware, specific tool chains are also available. So, which enables easy for development of the systems. Then, normally it provides a cross compilation support using this embedded C provides cross compilation support depending on the hardware and embedded target board what are using. So, embedded C will act as backbone for firmware development for all the modern smart devices and embedded products. So, it is a core requirement for embedded system developers who are working on consumer electronics, devices, IoT applications, and combination. So, so that is why it enables to build and optimize reliable and power embedded solutions, which you can never ever achieve by using conventional C. So, having introduced about the importance of embedded C programming, we'll get into the discussion of this unit. Memory layouts. Already, you know, the fundamentals of variables and constant IO operations. So these things are discussed in conventional C programming. So almost everything will be repeated as such here in embedded C programming also. Here the most important concept is memory layouts. We will discuss about memory layouts. Then we'll come back to those other parts there. Okay, so actually you can see this picture inside this the layout of your RAM. So in memory layout normally refers to actually this is your RAM. Okay, so this is your RAM. So your RAM memory starts in 0. That's here, and it keeps on increasing here. So the topmost memory location. So this will be in 0x. Yep. Yes. So okay, as you know that it represents the memory in terms of hexadecimal variable, right? So hexadecimal variable. So we used to use the prefix 0x representing hexadecimal numbers. So it's a topmost address will be in terms of FFH. So depending on how much bit RAM you're using, it will be increasing it. So that it starts in the port segment, initialized data segment, uninitialized data segment, deep memory. Then at the top, you have the stack memory. So this is the memory organization of your RAM. So you can ask, what is its importance in the embedded system? So the embedded system has a limited amount of RAM and ROM resources. So efficient memory utilization may directly affect the performance of the system, particularly in terms of reliability and power consumption. So this has to be taken very important care. And also you can see that the first segment, the core segment. So it stores the text where the program will be stored here. Then initialized data segment holds the variables that are supposed to initialize will be available here. The uninitialized data segment stores the uninitialized variables. So those things will be stored here. Okay. And a heap memory is meant for dynamic memory allocation. Hope you remember you might have used the functions like mlog, clog, free, etc. So those functions managements are being using this heap memory allocation for direct memory access using pointers, these kind of things. Then you can see that stack memory. So stack memory handles local variables and I mean local function calls. Then stack overflow. Because when stack gets overflow, it leads to embedded device crashes as well. So you can see that this heap memory will be going upwards. Heap memory will be going upwards. Stack memory will be going downwards. So these are the major components in your memory layer. So let's recall, you can see that in the core segment you will be storing your program. So the program what you have written will be here. The initialized data segment what you have initialized variable. For example, I'm writing int x is equal to 10. So this is the initialized variable. So this variable will be stored here. In uninitialized data segment, uninitialized variable. For example, I'm writing int y, simply y. So it's not initialized. So these things will be available in this segment. Then heap memory, you know that uses the dynamic memory location in malloc, etc. So when this will be allotting some space for heap, when it gets overflowed, then it increases the memory in this case. You know that already I mentioned the memory address starts from here. H, and it extends up to this top of the stack. Okay. Here, it ends with like the f. So when the stack gets filled, we'll be using this space. The heap memory gets filled, we'll be using the space of this. So this is the typical memory layout of any C program. So normally, not only meant for embedded C program, but for elementary C programs also, this is the case. Okay. Yeah. So just to recall again, the code segment, it uses the machine code like a function like main. So normally we'll be writing a program that starts with the main. Okay. So the function main also is residing in the code segment. And most important is it's a read-only space, because once you open the code in that space, you cannot rewrite it over it. So it's a read-only memory. Okay. But you can create multiple instances of the same program to answer memory also. So this is about the first segment, the code segment. Then initialized data segment, as I mentioned, that this it has the static and global variables. So we already mentioned that in the initialized we are writing int x is equal to 0. Okay. So let's say that static int y is equal to 10. So these are initialized variables. So those things are available in the data segment part. Okay. So then it can also be divided into further read-only area and read-write areas. Also, you can divide this accordingly. Okay. And also, most important thing is you can also be able to alter the variables during runtime. Okay. It is not a purely read-only data segment. You can also, because once you initialize x is equal to 0, you have the liberty for modifying the value to the later point of the code. So this is the second segment. That is the initialized data segment. Then coming to the next part is uninitialized data segment. So hope you remember what you had in the segments. So we had so then we have the heap segment. So this heap segment used for dynamic memory allocation. So hope you remember what we had in this memory layout. Um, so first we got the course, we got the core segment, then initialized data segment, then uninitialized data segment. So now we have the heap segment. So in the heap segment, what we have is we have the memories are allotted in malloc and CLR. Typically, as mentioned, this will be growing upwards. The memory will be growing upwards. But one thing we have to be very careful that once memory is allotted, it has to be manually, you have to free them automatically. We use malloc for allotting memory. We use free function to deallocate memory. So this is very important to prevent memory leaks in the system. So this is about heap segment. Then finally, the stack segment. This is the top part. You know how which stack works. Last in first out. So whichever in our memory layout, the stack is at the top. Okay, so you have this. The stack will be at the top. Here you have the stack. So once this memory is full, this will be growing downwards. Okay. So it works on the last in first out principle. So whichever element we are inserting at the last part, so that will be coming out first. But when the stack gets overflowed and the limit of the stack exceeds, we come across the issue called as a stack overflow. So you have to be very careful in managing these things. So each time when a function is being called, function is being returned, and it uses the stack memory location to store the local variables, to store the program counter. And the local variables also use the stack memory because when the function goes out of scope, the stack memory gets cleared automatically. So this is about the stack memory location. So it will start from another. It starts from the address like a. It starts from the address like a. We have 0xF at the top. Here is 0x00. So stack will be growing towards the word address. Okay, and manages automatically in last in first out fashion. So this is about the memory layout. So just to summarize what we discussed. So memory layouts are very important for embedded system developers, particularly embedded systems operating the limited resources. It is very crucial because embedded systems normally have less amount of RAM and ROM, and so it is we have tried efficient use of that. We're using the memory carefully. So efficient memory utilization also have a direct impact on the system performance, particularly reliability and power consumption. Then as to ask how the power consumption also coming into because when you're putting up into periodic access to memory locations, the power consumption gets increased. So this could also be significantly reduced when using proper memory layouts in the system, but a system. Okay, and also it reduces the memory footprint. So what is the footprint? This footprint refers to the amount of RAM and ROM we are using for the embedded system. How much amount of RAM and ROM we use it for embedded application. So that defines your memory footprint. So this also significantly get reduced when you use a proper memory layout. Okay. And this is highly critical for real-time low power embedded application because embedded systems are highly resource constrained, particularly for low power embedded application. Significant cache should be considered the memory layouts. Okay, and it helps to differentiate. We already discussed about what is user space, kernel space, etc. It is enables to distinguish the user space and kernel space exactly, and it's also a highly essential tool for firmware developers, device developers, and embedded software developers. So students who are getting up into this field, this is an efficient, basic, fundamental thing for safe embedded product development. Thank you very much.